Oh, it's just warming up for this SN1 or SN2 practice. So we got some alkyl halides, we got some nucleophiles, and we have to decide, is the process SN1 or SN2? Some good practice. We got to warm up. All right. So take a minute, pause the video, decide for yourself, and then we'll get together to discuss. Oh, yeah, still warming up. All right. Got my marker arm warmed up. Now I'm ready. Okay. So what do we got here? We have a primary alkyl halide. What about primary alkyl halides is true? They can't form carbocations. They can't do it. No carbocations are allowed. So that means that they have to undergo SN2 reactions only if a reaction can occur. So here we have a primary alkyl halide, and we have a strong nucleophile. How do we know that's a strong nucleophile? Because it's a salt. The sodium is positively charged. The OCH3 is negatively charged. So this is nucleophilic substitution. We have a primary alkyl halide, that's good at SN2. We have a strong nucleophile. Strong nucleophiles don't wait around. Also good for SN2. So that's going to produce the SN2 product. All right. How about this next one? This next one, we have a primary alkyl halide, and we have this was a strong nucleophile. This is a weak nucleophile. It's uncharged and it's oxygen. So weak nucleophiles, they do wait around. They're not strong enough to just force an SN2 reaction. They have to wait for a carbocation. Is a carbocation ever going to form? No, it's not, right? Because primary alkyl halides never form carbocations. So we have something that won't form a carbocation with something that will only react with a carbocation. So it turns out that this is actually no reaction. We're not going to get any reaction if we have a primary alkyl halide and a weak nucleophile. Okay, great. You did so good on that. What about this next one? All right, this next one, we have a tertiary alkyl halide and a very strong nucleophile. Strong nucleophiles don't wait around unless they can't reach the antibonding orbital, the sigma star. This is a tertiary alkyl halide. Those can only undergo SN1 reactions because they're too sterically hindered. So this is going to be an SN1 reaction because it's too sterically hindered around that alkyl halide. What about this one? We have a weak nucleophile, tertiary alkyl halide. Still going to be SN1 because that carbocation will form. When this leaves, that'll leave, forming the tertiary carbocation, the most stable type of carbocation. And then it doesn't matter if we have a weak nucleophile or a strong nucleophile. Either of those are going to add their electrons to that positive charge. I'll just show it with this one. That's what it sounds like when electrons move. All right, we'll do the next two in a minute. We're back. All right. So we have this molecule, treating it with the two different sets of conditions, our strong nucleophile, our weak nucleophile. What is this? This is a secondary alkyl halide. So you have to decide two things. One, is it SN1 or SN2? And then secondly, I want you to predict the products. So go ahead and do both of those things. Boop. Paused. Boop. Restarted. Okay. So we have our strong nucleophile. Strong nucleophiles don't wait around. And this is a secondary alkyl halide. So there is some access to that antibonding orbital, the sigma star. So this is going to be an SN2 reaction. The OCH3 will add to the backside of this alkyl halide. So what's going to happen there? That means the stereochemistry in that position is going to change. So we'll have OCH3 as a wedge. Nothing happened to that methyl group, so that stays the same. What about this one down here? This was a weak nucleophile. Weak nucleophiles need to wait until we have the carbocation form, the stronger electrophile. So this is going to be SN1. So that is going to leave. That would produce this carbocation where the nucleophile can either add to the top or the bottom. It's going to add to both. And ultimately, the product, so there's our positive charge. When it adds to the top, it would be a wedge. When it adds to the back, it would be a dash. But to represent both of those stereoisomers, we're going to do the little wavy thing. So nothing happened to this stereocenter. It stays the same. But the OCH3 is equal parts on the front and the back. So that's what that wavy bond describes. All right. Hope that was fun.